Welcome you all. In this video, we will see the definition of eigenvalues and eigenvectors and then the properties of eigenvalues. First, we will see the definition of eigenvalues and eigenvectors. Let A be an n by n matrix. A number lambda is called an eigenvalue of A if there exists a non-zero vector capital X equal to x1, x2, xn such that Ax equal to lambda x, and this x is called an eigenvector corresponding to the eigenvalue lambda. If x is an eigenvector corresponding to the eigenvalue lambda of A, then alpha x, where alpha is any non-zero number, is also an eigenvector corresponding to lambda. Let x be an eigenvector corresponding to the eigenvalue lambda of A, then Ax equal to lambda x, so that A minus lambda of x equal to 0. Thus, x is a non-trivial solution of the system of homogeneous linear equation. Hence, determinant of A minus lambda equal to 0, which is the characteristic equation of A, and the roots of this equation give the eigenvalues of capital A. Hence, the eigenvalues are also called the characteristic roots. First, we will see the first property. Let x be an eigenvector corresponding to the eigenvalues lambda 1 and lambda 2, then lambda 1 equal to lambda 2. So by the definition, Ax equal to lambda 1x and Ax equal to lambda 2x. So by equating these two, since x is a non-zero vector, lambda 1 minus lambda 2 must be equal to 0. Hence we will get lambda 1 equal to lambda 2. In the second property, we will take a square matrix and then the sum of the eigenvalues equal to the sum of the diagonal elements, which is nothing but the trace of A, and the product of the eigenvalue of capital A is determinant A. So first we are taking a matrix, square matrix, n by n matrix, capital A. So the eigenvalue are the roots of the characteristic equation. So from 1 and 2 we will write like this. So by putting lambda equal to 0, we will get A n equal to determinant A. Thus, by the sum of the roots, we will end up with the trace of A. And the product of the eigenvalue is nothing but the product of the roots, which is nothing but the determinant of A. The eigenvalues of A and its transpose are the same, which will be seen in property number 3. So to show that the eigenvalues of A and A transpose are same, it is enough to say that A and A transpose have the same characteristic polynomial. So we get A minus lambda is determinant equal to its transpose, so which can be written like this. So we are getting the A and A transpose have the same characteristic polynomial. In property 4, if lambda is an eigenvalue of a non-singular matrix A, then 1 by lambda is an eigenvalue of A inverse. So we have Ax equal to lambda x, so multiplying A inverse on both sides, we end up like this. So 1 by lambda is an eigenvalue of A inverse. So in the corollary, we will see that if lambda 1, lambda 2, lambda n are the eigenvalues of a non-single matrix A, then 1 by lambda 1, 1 by lambda 2, etc., 1 by lambda n are the eigenvalues of A inverse. In property 5, if lambda is an eigenvalue of A, then k lambda is an eigenvalue of Ka, where k is a scalar. So we have Ax equal to lambda x, so considering Ka of x, so k into Ax, so Ax, in the place of x we are substituting a lambda x, so k lambda is a scalar, so we can take out, so k lambda is the eigenvalue of the matrix Ka. Property 6, if lambda is an eigenvalue of A, then lambda power k is an eigenvalue of A power k. So for that, first we will consider A square x, which can be written as Ax. So in the place of x we can substitute lambda x. So since lambda is a scalar, we can take it out. So in the place of Ax, again we are substituting lambda x, so we will end up like lambda square x. So lambda square is an eigenvalue of A square. So similarly, proceeding like this, we will get lambda cube is an eigenvalue of A cube, etc. Lambda power k is an eigenvalue of A power k. So if lambda 1, lambda 2, lambda n are eigenvalues of a non-singular matrix A, then lambda 1 power k, lambda 2 power k, etc. lambda n power k are the eigenvalues of A power k for any positive integer k. So in property 7, we will see that eigenvectors corresponding to the distinct eigenvalues of a matrix are linearly independent. So lambda 1, lambda 2, lambda k be the distinct eigenvalues and xi be the eigenvector corresponding to the lambda I. So axi equal to lambda xi where I ranging from 1 to 2. So we have to show that these vectors are linearly independent. So suppose we are taking this as linearly dependent. So not all the constants are 0. So among such relation we are choosing one of short length j. So after j it's equal to 0. So we are multiplying matrix A throughout. So we will get like this. So in the place of ax1, lambda 1 x1, ix2, lambda 2 x2, j xi. So multiplying equation number 2 by lambda 1 and subtract from 3, we will get like this. So since lambda 1, lambda 2, lambda j are distinct, alpha 2, alpha 2, 3 alpha j are non-zero, we have like this. So alpha I lambda 1 minus lambda I into xi not equal to 0, which gives a relation of length j minus 1 which is less than j, so we are getting a contradiction. So our assumption is wrong, hence the eigenvectors are linearly independent. So the characteristic roots of a Hermitian matrix are real, which will be seen in property number 8. So a Hermitian matrix A equal to A bar transpose. So Ax equal to lambda x, so multiplying x bar transpose on both sides, then taking transpose on both sides, then taking conjugate on both sides, we will get like this. So in the place of Ax we are substituting lambda x. So in this place we are getting lambda equal to lambda bar, which means that lambda is real. So from this property we can say that characteristic roots of a real symmetric matrix are real. So in property 9, the characteristic roots of a skew Hermitian matrix are purely imaginary or 0. So lambda is a characteristic root of A means like this. Determine A minus lambda equal to 0. So Ia minus I lambda I equal to 0. Since A is a skew Hermitian matrix, A equal to minus A bar transpose. So from this equation we are getting I lambda is a characteristic root of Ia. Since A is skew Hermitian, Ia is Hermitian. So by previous property, I lambda is real, which means lambda is purely imaginary or 0. So from this we can say that the characteristic roots of a real skew symmetric matrix are either purely imaginary or 0. In property 10, we will see that if lambda is a characteristic root of a unitary matrix, then modulus lambda equal to 1. So what is unitary matrix? So in unitary matrix, A bar transpose it A equal to A bar transpose equal to I. So from this Ax equal to lambda x, we are taking conjugate and transpose on both sides. And substituting the value, we will end up lambda bar into lambda equal to 1, which implies modulus lambda equal to 1. So from this property, we can say that if lambda is a characteristic root of an orthogonal matrix A, then modulus lambda equal to 1. So 0 is an eigenvalue of A if and only if A is a singular matrix. So the eigenvalues are the roots of the characteristic equation. So 0 is an eigenvalue implies increment A equal to 0, which is A is a singular matrix. So in property 12, we will say that if A and B are two square matrices of the same order, then AB and BA have the same eigenvalues. So we are taking lambda as a characteristic root of AB and x is the characteristic vector corresponding to lambda. So ABx equal to lambda x. So multiplying B on both sides. So we will get BA Bx equal to lambda Bx. By putting y equal to Bx, we will get BA y equal to lambda y. So lambda is the eigenvalue of BA. So which implies lambda is an eigenvalue of both AB and BA. So they are having the same eigenvalues. So if P and A are n by n matrices and P is a non-singular matrix, then A and P inverse P have the same eigenvalues. That is, the similar matrices have the same eigenvalues. To show that, it is enough to show that they both have the same value, it is enough to show that they have the same characteristic polynomial. So determinant b minus lambda, where b is nothing but b inverse ap. So by putting like this, we will get the determinant, both determinants will be same. So we will say that both have the same characteristic polynomial. If x1 and x2 are the eigenvectors corresponding to an eigenvalue lambda, then ax1 plus bx2 is also an eigenvector corresponding to lambda. Since x1 and x2 are eigenvector corresponding to an eigenvalue lambda, ax1 equal to lambda x1, ax2 equal to lambda x2. So a into ax1 equal to lambda x1 and a into bx2 equal to lambda bx2. So by adding these two, we will get lambda into ax1 plus bx2 is nothing but a into ax1 plus bx2. So ax1 plus bx2 is an eigenvector corresponding to it. So the final property we are going to see that if lambda is a characteristic root of A, then f of lambda is a characteristic root of the matrix f of capital A, where f of x is any polynomial. So we are taking f of x as any polynomial. So f of A will be like this. Since lambda is an eigenvalue, lambda power n is also an eigenvalue of A power n. So we are writing like this. So multiplying the first value by a0, second value by a1, like that an minus 2. So adding the above equation, we will end up like this. So adding a and x on both sides, we will get f of a into x equal to f of lambda into x, which means that f of lambda is a characteristic root of the matrix of A. Thank you.